Well, the ideas, basically, ideas which I formulated in my first year as a graduate student in Cambridge. I did my undergraduate work in mathematics in London, and I had a colleague, Ian Percival. We used to discuss things like computational and logical systems quite a lot. I'd heard about Godels' theorem. I was a bit worried by the idea that it seemed to say there were things in mathematics that you could never prove. And so when I went to Cambridge as a graduate student, I went to various courses. You see, I was doing pure mathematics. I was doing algebraic geometry of a sort, a little bit different from what my supervisor and people, but it was algebraic geometry. Yeah. And I was interested, I got particularly interested in 3 lecture courses that were nothing to do with what I was supposed to be doing. One was a course by Hermann Bondi on Einstein's general theory of relativity, which was a beautiful course. He was an amazing lecturer, brought these things alive, absolutely. Another was a course on quantum mechanics, given by the great physicist Paul Dirac. Very beautiful course in a completely different way. He was very kind of organized and never got excited about anything, seemingly. But it was extremely well put together, and I found that amazing too. The third course that was nothing to do with what I should be doing was a course on mathematical logic. And I got, as I say, my discussions with Ian Percival.
Was the incompleteness theorem already deeply within mathematical logic space? Were you introduced to it?
I was introduced to it in detail by the course by Steen. And it was 2 things he described which were very fundamental to my understanding. One was Turing machines and the whole idea of computability and all that. So that was all very much part of the course. The other one was the Gödel theorem. And it wasn't what I was afraid it was, to tell you there were things in mathematics you couldn't prove. It was basically, and he phrased it in a way which often people didn't. And if you read Douglas Hofstadter's book, he doesn't, you see. But Steen made it very clear, and also in a sort of public lecture that he gave to a mathematical, I think maybe the Adams Society, one of the mathematical undergraduate societies, and he made this point again very clearly, that if you've got a formal system of proof, so suppose what you mean by proof is something which you could check with a computer. So to say whether you've got it right or not, you've got a lot of steps. Have you carried this computational procedure, well, following the proof, steps of the proof correctly, that can be checked by an algorithm, by a computer. So that's the key thing. Now what you have to, now you see, is this any good? If you've got an algorithmic system which claims to say, yes, this is right, this you've proved it correctly, this is true. If you've proved it, if you made a mistake, it doesn't say it's true or false, but if you've done it right, then the conclusion you've come to is correct. Now you say, why do you believe it's correct? Because you've looked at the rules and you said, well, okay, that one's all right. Yeah, that one's all right. What about that? Oh, I'm not sure. Oh, yeah, I see why it's all right. Okay. You go through all the rules. You say, yes, following those rules, if it says, yes, it's true, it is true. So you've got to make sure that these rules are ones that you trust. If you follow the rules and it says it's a proof, is the result actually true?
Right.
And that your belief that it's true depends upon looking at the rules and understanding them. Now, what Gödel shows, that if you have such a system, then you can construct a statement of the very kind that it's supposed to look at, a mathematical statement, and you can see by the way it's constructed and what it means that it's true, but not provable by the rules that you've been given. And it depends on your trust in the rules. Do you believe that the rules only give you truth? If you believe the rules only give you truth, then you believe this other statement is also true. I found this absolutely mind-blowing. When I saw this, it blew my mind. I thought, my God, you can see that this statement is true. It's as good as any proof because it only depends on your belief in the reliability of the proof procedure. That's all it is. And understanding that the coding is done correctly. And it enables you to transcend that system. So whatever system you have, as long as you can understand what it's doing and why you believe it only gives you truths, then you can see beyond that system. Now, how do you see beyond it? What is it that enables you to transcend that system? Well, it's your understanding of what the system is actually saying and what the statement that you've constructed is actually saying. So it's this quality of understanding, whatever it is, which is not governed by rules. It's not a computational procedure.
So this idea of understanding is not going to be within the rules of within the formal system.
Yes, you're only using those rules anyway, because you have understood them to be rules which only give you truths. There'd be no point in it otherwise. I mean, people say, well, okay, this is one set of rules as good as any other. Well, it's not true. You see, you have to understand what the rules mean. And why does that understanding of them mean give you something beyond the rules themselves? And that's what it was. That's what blew my mind. It's somehow understanding why the rules give you truths enables you to transcend the rules.
So that's where, I mean, even at that time, that's already where the thought entered your mind that the idea of understanding, or we can start calling it things like intelligence or even consciousness, is outside the rules.
Yes. See, so I've always concentrated on understanding. You know, people come and point out things. Well, we know, what about creativity? That's something a machine can't do, is create. Well, I don't know. What is creativity? And I don't know. And, you know, somebody can put some funny things on a piece of paper and say that's creative, and you could make a machine do that. Is it really creative? I don't know. You see, I worry about that one. I sort of agree with it in a sense, but it's so hard to do anything with that statement. But understanding, yes, you can. You can go see that understanding whatever it is, and it's very hard to put your finger on it. That's absolutely true. The thing about Gödel's theorem, you see, I used to have a colleague when I was at undergraduate, Ian Percival, who also became a scientist later on, and we talked about logic and, you know, how you could make these kind of mathematical systems which worked out logic. And I'd heard about this Gödel's theorem, which seemed to say that there were things in mathematics that you just couldn't prove. And I didn't like that idea. But when I went to this course by Steen, and he explained what it really says. And what it says is, suppose you've got a method of proving things in mathematics. And when I say things, I mean things with numbers. The one famous example is Fermat's last theorem. There's the Goldbach conjecture, which isn't yet proved, that every even number bigger than 2 is the sum of 2 prime numbers. That's the sort of example of the thing. It's just sort of mathematical things about numbers, which you can see what they mean, but it may be very difficult to see whether it's true or untrue. But the idea often is, in mathematics, you've got a system of methods of proof. And the key thing about these methods of proof is that you can have a computer check whether you've done it right. So these rules, you know, they could be adding A and B, it's the same as B and A and things like that. And if you give you say to the computer, say, here is a theorem like Goldbach conjecture, and you see whether it can be proved, and you say, maybe I've got a proof, and this follows these steps, and you give it to the computer, and it says, yep, you've done it right, it's true. Or maybe it would say, you've done it right, and it's not true. Or it may not say anything, it might just go on forever. But these are the sort of outcomes. And the point about it is that if you believe that these procedures do give you a proof, in other words, that if the algorithm says, yeah, it's true, then you believe that it is true because you've understood all the rules. You looked at the first one and said, yeah, that's okay. You looked at the second one and said, yeah, I see. Okay, that's great. And you go all the way down. And as long as you're convinced all those rules work, then if it says yes, that's something you believe. Okay. Now what Gödel shows is he constructs a very specific sentence, a statement, which is a number thing, like the Fermat's last theorem or something, a thing about numbers, which what he shows is if you trust this algorithm for proving mathematical things, then you can see by the way it's constructed that it's true. But you can also see, by the way it's constructed, that it cannot be proved by this procedure. Now, this was amazing to me because it tells me that, okay, you cannot formalize your understanding in a scheme which you could put on a computer. You see, this statement which Gödel comes up with is something you can see on the basis of the same understanding that allows you to trust the rules, that it's true, but that it's not actually derivable by the rules. You see it's true by virtue of your belief in the rules. And this to me was amazing.